Why do some faces instantly seem more attractive than others? Our brains make quick judgments about beauty in a blink of an eye, often before we even realize it. Studies show we're naturally drawn to symmetrical faces. That's true. But why? Scientists think that it's not just about looks. Symmetry signals health, strength, and even genetic stability. But this is just the tip of the iceberg. Hello, my name is Lilith, and today I'm inviting you to travel back 13.8 billion years across time and space to discover how symmetry shaped the universe's foundations until the day it broke, giving rise to everything we know. Symmetry is not just a feature of Earth itself, but a fundamental principle shaping objects, patterns, and living organisms. It appears almost everywhere, influencing both structure and function, from the microscopic scale of molecules to the vast formation of landscapes.
Sunflower seeds spiral with the precision of Fibonacci's sequence, each turn quietly solving the puzzle of space and energy. Nautilus shells coil in the same logarithmic rhythm, a slow echo of the mathematics that shape the universe. Fern fronds unfold in fractal repetitions, showing that what appears simple is in fact an elegant solution, nature's secret algorithm, perfected by billions of years to combine strength, efficiency, and beauty. Snowflakes form intricate six-fold designs, while salt crystals grow into perfect cubes, with their structures dictated by molecular forces. Even Earth's landscape exhibits symmetry, with mountain ranges forming sweeping arcs due to tectonic collisions and ocean currents flowing in mirrored loops guided by the planet's rotation. From the chaotic swirl of cosmic dust and molten rock that formed Earth billions of years ago, order gradually emerged. As the planet cooled and life took hold, nature began to weave intricate patterns into its creations.
These patterns, rooted in symmetry, became the foundation for how organisms grow, move, and survive. Scientists have pinpointed 4 key symmetry types that play a central role in organizing patterns and structures.
A jellyfish, for example, has tentacles radiating outward in all directions, allowing it to respond to stimuli from any angle. When body parts are arranged around the central axis, a common feature in marine life, it's called radial symmetry. Interestingly, if a jellyfish loses one of its tentacles, it can still appear symmetrical due to its ability to regenerate and maintain balance in its overall structure. Another form seen in nature is rotational symmetry, which allows objects to maintain their appearance when rotated by specific angles. A starfish remains visually unchanged when rotated by 72 degrees, a characteristic made possible by its 5 arms. Translational symmetry appears when a pattern can be moved along a direction without changing its appearance. This is often seen in wallpaper designs and honeycombs, where repeating units extend seamlessly. The striped pattern on certain snakes, such as coral snake, follows this principle, helping with camouflage. And finally, one of nature's most efficient designs, shaping everything from how animals move to how they perceive the world, bilateral symmetry. It allows streamlined movement, precise coordination, and the development of complex behaviors. This symmetry is why most animals, including us, have a clear front and back, left and right, and defined head with sensory organs concentrated at the front. Predators rely on it to chase prey with speed and accuracy, while prey animals use it to react swiftly and escape danger. Whether running, swimming, or flying, this coordination ensures balance, stability, and precise control.
Our eyes, ears, and nostrils are arranged symmetrically, enhancing perception and depth awareness. Even our internal organs, though not perfectly mirrored, follow an overall balanced layout for efficient function. Since we are built this way, our understanding and perception of the world naturally depend on it, shaping the way we think.
Yet, as in the universe, symmetry here too breaks for the sake of efficiency. Our human brain, though symmetrical in structure, divides tasks between hemispheres.
However, this balance isn't absolute. Regions like Broca's area for speech are typically dominant on one side, and left-handed individuals may exhibit less rigid hemispheric specialization for some functions and often use both hemispheres more evenly.
This slight asymmetry can improve biological function, showing that while bilateral symmetry is a key feature of many life forms, small deviations can contribute to evolutionary change. At the very blueprint of life, DNA follows a strict symmetrical structure. Twisting double helix is not only functional but also symmetrical. This special kind of symmetry is called helical symmetry. Repeating spiral shape helps DNA to stay stable, while also making it easy to unfold and copy when needed. So its symmetry is all about balance, beauty, and usefulness. This allows for flawless replication, preserving genetic information across generations.
And you know what is very important? That our DNA's double helix twists to the right. And the reason for that is something called chirality.
Imagine holding two identical gloves. No matter how you turn, the left glove will never fit your right hand unless you turn it inside out. Though that feels a bit like cheating, doesn't it?
Try to do the same with your shoes. Or when you play Tetris, you get these two blocks and no matter how hard you try, they just don't fit. This type of asymmetry, chirality, is quite common, you see, and not only in geometry and mathematics, but in chemistry, physics, and molecular biology.
In molecules, chirality occurs when an atom, usually carbon, is connected to four different groups, creating two mirror images, left-handed and right-handed forms. Even though they have the same atoms, they can behave very differently, just like a right hand doesn't fit well in a left glove.
Now imagine stepping into a kitchen to make a perfect cup of tea with a lemon slice. Suddenly, you realize something extraordinary. The lemon smells like an orange. The first thought of a healthy person should not be what I will say now, but hear me out.
Proteins are built from amino acids, but only left-handed amino acids work. Right-handed versions exist, but they are useless. If life had evolved using right-handed amino acids instead, you, me, and every living thing on Earth would be built in reverse.
So the chemical responsible for the lemon smell is called laminin, and its mirror image, chiral twin, gives oranges their characteristic aroma. So even though the molecule responsible for scent is the same in both lemons and oranges, their aromas are quite different.
Now, maybe one day we will stumble upon a world where life is built on right amino acids instead of our familiar left amino acids. The food might look almost identical: lemons, apples, even the perfect cup of coffee.
In this mirror world, the very molecules that give food its signature scent are chiral. Despite the visual similarities, the chemical signals are off, making everything seem a bit alien.
But here's the interesting part. When you take a bite or a sip, your body, finely tuned by evolution, won't be fooled. It simply won't recognize the odd chemistry, and you might end up with some truly bizarre digestive surprises. This year, at Paris's Institut Pasteur and California's Asilomar, scientists debate a moratorium on full mirror bacteria, self-replicating life built from reversed molecules, resistant to our antibiotics, phages, and predators, capable of unsettling ecosystems like cyanobacteria on steroids. Mirror peptides are already in trials, hinting at allergy-proof drugs and novel therapeutics. But ethicists warn one lab leak and we could witness ghost life rewriting biology's rules. Chirality is a whisper of broken symmetry, a cosmic fingerprint hinting at deeper rules yet to be discovered. It determines why your body works, why DNA spirals in one direction, and why the universe isn't perfect. The smallest twist in nature, the tiniest violation of symmetry, is the reason we exist at all.
But why does life insist on left-handed amino acids? Well, we don't know. Perhaps it was a cosmic accident, an ancient bias set by the molecules that first formed in space. Meteorites that have crashed on Earth contained more left-handed amino acids than right-handed ones, suggesting that this molecular asymmetry originated before our planet formed.
At the quantum level, neutrinos, ghost particles that pass through us by the trillions, always spin in one direction relative to their motion. No right-handed neutrinos, or as they are called antineutrinos, have ever been found. Why? We don't know that either. Even the weak nuclear force, the very force that powers stars, has a preference. This means it treats matter and antimatter differently, preferring certain decay processes over their mirror image counterparts.
And again, we don't know why. It is the only fundamental force that does this, and it may be linked to one of the greatest mysteries in physics: why there is something rather than nothing.
In the first moments of the Big Bang, the universe was nearly uniform. Energy, matter, and even the forces of nature were distributed in a way that was approximately the same in all directions. This is called isotropy and homogeneity. For a fleeting moment, it was in a perfectly symmetrical state. From quarks to leptons, everything existed in harmony.
But perfection doesn't last forever. As the universe evolved, symmetry broke and disorder took hold, leading to entropy. 13.8 billion years later, in 1915, Emmy Noether uncovered something profound. Symmetry wasn't just a beautiful pattern in nature. It was the key to understanding the universe itself.
She discovered that every fundamental symmetry in physics is tied to a conservation law. The unchanging nature of space ensures momentum is preserved. The symmetry of rotation safeguards angular momentum, and the steady passage of time guarantees that energy never just vanishes.
But what happens when symmetry isn't perfect? That's where things get more interesting. A tiny asymmetry, known as CP violation, that favored matter over antimatter, was enough to prevent everything from vanishing in a flash of annihilation. Instead of a universe of pure energy, a small excess of matter remained.
As the universe expanded and cooled, fundamental forces and particles settled into new states, breaking earlier symmetries. But this wasn't chaos, it was evolution.
Gravity was the first force to break away. Though the weakest of the fundamental forces, gravity sculpts galaxies, holds planets in orbit, and even influences the flow of time.
Like other forces, gravity doesn't push or pull, it bends space itself, creating the cosmic stage for everything that follows. Yet, it remains an enigma, refusing to fit neatly into quantum world. Perhaps this is because it was the first to separate, the first to break away from the perfect symmetry of early universe.
Next came the strong nuclear force, the glue that holds the universe together. It binds quarks into protons and neutrons and holds nuclei together. Without it, matter would simply dissolve into a sea of particles.
Its beauty lies in color symmetry, the foundation of quantum chromodynamics. Quarks come in three types of color charge, not literal colors but quantum properties, and the strong force ensures that they always combine into perfectly balanced, color-neutral states.
With the strong force in place, the weak nuclear force emerged, bringing transformation. Unlike the strong force which binds quarks together, the weak force allows particles to change their identity. It drives the nuclear reactions that power stars and sustain life.
It also played a role in one of physics' greatest mysteries, the imbalance between matter and antimatter. In the universe's earliest moments, weak interactions favored matter over antimatter. Without this tiny asymmetry, everything would have vanished in a flash of energy. Instead, this small imperfection set the stage for the universe as we know it.
Finally came electromagnetism, granting the cosmos light and chemistry. It governs everything, from the glow of stars to the charge in your phone.
Unlike gravity, which only attracts, electromagnetism can both pull and push, holding atoms, molecules, and even galaxies together. Its deep symmetry, gauge invariance, ensures that no matter how fields shift, the laws of physics remain unchanged. It is the force that bridges the quantum world and the cosmic expanse, carried everywhere by light.
What began as a single, elegant force fractured into four, but they never lost their connection. Each force still carried the imprint of the original unity, and its symmetries continue to guide everything in the universe. A step further, physicists have proposed the idea of supersymmetry. This theoretical framework suggests that every fundamental particle has a corresponding superpartner with similar properties, but a different intrinsic spin. According to theory, metaparticles, called fermions, like electrons and quarks, would have superpartners that are bosons, the force-carrying particles, like photons and gluons, and vice versa.
While we haven't yet found evidence for these superpartners, supersymmetry remains compelling. It could explain why particles have the masses they do, and offer a bridge toward unifying quantum mechanics with gravity through broader theories such as string theory.
In May 2025, a paper arrived like a crack in the wall. A team of physicists proposed a framework of quantum gravity rooted in four one-dimensional gauge symmetries, the very mathematical language that holds the standard model together.
For the first time, gravity was written in the same script as the other forces. If confirmed, it would be more than a unification. It would be a step toward the much-desired theory of everything, a single symmetry blueprint tying together the cosmos from quarks to galaxies. In July this year, during CERN's Large Hadron Collider beauty experiment, scientists observed charge parity or CP symmetry breaking in beauty baryon decays, proof that matter and antimatter don't play fair, explaining why our universe is packed with stuff like us instead of cancelling out to nothing.
Such a theory could reveal how the universe's laws held steady at the Planck scale, where space-time itself foams and shatters. It could rewrite what we know about black holes, the fate of information, and the very first tick of the Big Bang. Symmetry began this story, and perhaps, at its deepest level, symmetry will finish it. The dance between order and chaos goes beyond physics. It shapes who we are. When we ask why there is something rather than nothing, we see how symmetry and chaos work together, proving that even imperfections have purpose. As we explore the universe, we're not just observing a perfect system, we're part of a dynamic, ever-evolving story of balance and surprises. Thank you for your time. See you in the next video.